there are a couple of observations that we need to make using rules for differentiation. The first one is that when you differentiate, you need to get the gradient of the tangent at a point. Clearly, if there is a discontinuity, I can't draw a tangent because there would have been a hole, and so there would have been no gradient. What I've just said is very well illustrated over here. Can you see that there is a discontinuity exactly when x is 2? In other words, this graph has a constant gradient as it was a straight line, but there is no gradient when x is 2, so I cannot find the derivative at x is equal to 2. The next rule is a nice rule. It says that if I have a constant for y, in other words, I have a horizontal line, its derivative is 0. You can see from my diagram that it doesn't matter where I would draw my horizontal line, that the gradient of this horizontal line would have been 0. So as my y is a constant, the derivative is 0. On a straight line, which is my linear function, I have a constant gradient, and my gradient can be found here at m. As it is a constant gradient, I know that my gradient will always be the same. How do I know that I have a straight line? Well, my x is x to the 1. If you take a look at the diagram that I've given you, I've drawn a straight line. It has a constant gradient. This straight line, if I had written it out, would have been the line of y is equal to 2x plus 4. How am I going to know what the gradient is? Well, I would have taken a look over here at the 2. Can you see that it's very easy to see that gradient because it is the coefficient of x to the 1. Rule number 4 is a very important rule. This is going to give us a rule for finding the the derivative without the definition. Over here I've given you a graph of a parabola. You can see that the parabola is x squared plus 1. What I'm going to do in order to find the derivative function for this graph is I'm going to concentrate on the exponent of x. Can you see over here, if I have an exponent, then that exponent goes down as a coefficient factor, and then I minus 1 from my original exponent. In other words, for this graph, f of x, if I take a look at the derivative of this graph term by term, the derivative of f of x is going to be 2 times 1, which is 2x, and then if I minus 1 from the original exponent, I get x to the 1. 1 is a constant term, so that's like finding the derivative of a horizontal line, and that would have given me plus 0. In other words, the derivative is going to be 2x. And finally, for rule number 5, if I'm able to get my expression for my function into terms with all the x's in the numerators, I can find the derivative term by term, and adding up those terms, I've actually got my derivative. The best thing to do, though, is to look at a couple of examples. Taking a look at this function, you can see it is already broken down into terms. So that's starting to look good. But I have a problem because there is an x in the denominator. I also need to know what is the exponent when I have a square root. So before I even start finding the derivative, I need to get the expression for my function into a format that's going to be suitable to using my rule. So the function, can you note I'm still not finding the derivative, could rather have been written as 3, as x is a factor, and I take that factor up, that would have been x to the minus 1. And then instead of writing the square root, I could have said that that was x to the half. Now I've got my expression in standard form, and I'm ready to find the derivative. Working term by term, and remember, I'm using the following formula. I say that if I want to find the derivative of my function, and my function had started by looking like this, a times x to the p. Term by term, if I wanted to find the derivative, I would have taken a look at that exponent of x. The exponent becomes a coefficient factor. As I already had a coefficient of a, it becomes a times by p. And then the x's exponent, which was originally p, has a minus 1 taken away from it. Let's apply this now to the function that we have. So the derivative of f of x is going to be the following. I had a coefficient of 3. My exponent of x becomes a coefficient factor, so I must times that by minus 1. And my x's exponent, which was minus 1, must have minus 1 taken away from it. Moving on to my next term, my coefficient that I had originally was 1. A half must become a coefficient factor, and 1 times a half is a half. Then I write down my x, and from my original exponent, I minus 1. All that I need to do now is simplify both of these terms. Minus 3 times minus 1, 3 times minus 1 is minus 3, and x to the minus 2 is x squared in the denominator. And then, if I have got a half, then that means that the 2 is in the denominator, and x to the a half minus 1 is x to the minus a half, which means that it's also in the denominator. And x to the half in the denominator is going to give me the root of x.